So last time we had yt expressed in terms of psi naught, psi 1, psi 2, all the way up to wt minus j, and of course it could go up to infinity. So the way we express the model is we have phi of z yt equals wt. Yes. Characteristic polynomial multiplied by y sub t is wt. Divide by phi of z on both sides. And that would become uppercase psi of z wt. Good. So what we ended with last time is simply this polynomial. And that polynomial would be psi 1, psi 0 plus psi 1 L plus psi 2 L squared, psi j L raised j, and so forth, where L is simply the Lag operator. So let's go back to the example that we did a while ago. And I believe it was 1, well, yt was 0.8 yt minus 1 minus 0.1 yt minus 2 plus wt, or was it 0.8 plus 0.1?
0.8
Plus, okay. So this is what we did last time, and I want to go with what we did already because it is going to save some time finding the roots. Yes? Because we need the fees as in fees, to find the size. So the characteristic polynomial, we know how to get it. If we move that to this side, we'll have 1 minus 0.8 z minus 0.1 z squared. That simply is phi of z. Forget the 1 from here. Right, so we didn't know how to get to this, right? Remember? We first rewrote yt minus 1 in terms of yt. Yes, so we moved those to the other side and replaced the Lag operator by z. Good. So we had phi of z, and we solved the two roots of the characteristic polynomial. Was it 1.0099? So we found the roots of the characteristic polynomial, which was z1 equals 9.099, z2 1.099. If you know the z, how do we find the lambdas? 1 over z1, 1 over z2. negative.
Yeah. Right. That's why I thought.
That's what I thought, one of them
Yeah.
was negative.
Yeah.
Okay, so what did we get here, negative?
0.
I mean, isn't it supposed to be lambda too?
Yes. Negative
0.1091.
and
0.909.
so we have the lambdas. Now that we have lambda 1 and lambda 2, we can find all the constants that are here, right? Psi 0, psi 1, psi 2, and so forth. Well, I should go back and look at our derivation from last time. Hope this works. Psi 0 is C1 plus C2. Yes. Psi 1, C1 lambda 1 plus C2 lambda 2. Psi 2, C1 lambda 1 squared, C2 lambda 2 squared. Psi 3, C1 lambda 1 cubed plus C2 lambda 2 cubed.
So on and so forth.
You get the point now, yes. So dot, psi j is C1 lambda 1 raised j plus C2 lambda 2 raised j. So we've got to find the values of C1, C2, and the size so that we can express this as a series. So what is C1? C1 is lambda 1 over lambda 1 minus lambda 2. We derived this last time. C2 is lambda 2 with a negative divided by lambda 1 minus lambda 2. And that is all we would have for a second order model or a second order difference equation. If it is a third order difference equation, we would have C1, C2, C3, fourth, C1, C2, C3, C4, and so on. Okay, so now we have the values lambda 1 and lambda 2. Therefore, we must know C1 and C2. Let's go ahead and find C1 and C2 first, and then we can start finding the size. What is C1?
0.1078.
Is it right?
Yes.
And what is C2?
0.8922.
0.8922. So all we did is we took lambda 1, lambda 2, plugged it in the derived values for C1 and C2, we ended up getting that. So written psi 0, psi 1, psi 2, psi 3. Yes.
Is there like a specific formula for the, like beyond, just like for all the C's? Like if we had a C3 for a third order, would it be?
We will do that today. Patience. So psi 0, psi 1, psi 2, we can easily find it. So let's go ahead and find psi 0, psi 1, psi 2, psi 3. And psi j. You can evaluate all this using the table set function in the calculator. Do we know how? Instead of doing it, manually one thing at a time. No? There are two variables. Or we can use a matrix. No, let's just do it that way.
Also, we can't see anything you're doing up there.
You're not able to. No, we'll get there. I just want to write this expression. So psi j would equal to 0.1078. And what is lambda? 1.
And the one was negative 0.1099.
9j, C2 is
0.8922,
times
0.9099.
raised to j. Good. Now, that is our expression for psi j. And j is the unknown. I could replace the j by x, right? And use it in the calculator. So the TR-84 calculator is a nice thing called and we are going to use the table set function. So before you start evaluating the table, press second window. So second button followed by window. And you start the table at 0, leave it as is. Delta tables to change in table values, leave it as is. Over here, in general, the independent variable is x, the dependent variable is y. So from auto, I'm going to change it to ask. Good. Now, second mode to quit. Let's go back to y equals. I'm going to type in this expression. Make sure you put the parentheses properly. So 0.1078 times negative 0.1099 raised x plus 0.8922 times 0.9099 raise x.
Where did you go?
Good. So we have an expression which is the psi j in there. Now press second graph. And start plugging in values. We start with j equals 0. Enter. I get 1. That makes sense, right? It has to be 1. Then I plug in 1. I get 0.7997. When I plug in 2, I get 0.73997. 3.67197 4.61157. And you see where this is going, right? So we are evaluating discrete values using the table. Now, if you just want to see as to what happens in the long run, you can hit graph. Set the window, let's see, negative, you don't need negative, 0, maximum x value, let's go all the way up to 20. The minimum x y value has to be 0. The maximum that we will reach is 1. So 0 and 1. Did it work? Yeah. And 1. I'm trying to. Why am I getting 1 point?
You two.
Huh?
There's 2 points.
There are 2 points. This is weird.
They just look like little marks on my calculator, so.
That's so weird. I need to get the curve. What did you get? Did you get a nice curve?
Could you go back to the window real fast?
Huh?
Can you go back to that window thing?
Maybe it's because we only have 3 points.
That could be why, because of these.
Yeah. So if you changed it to not ask into auto.
Yeah. So we've evaluated this, so let's go back to second window. The table set, we'll change it to auto. It does it for us down, right? 0, 1, 2, 3, 4, 5, 6. Now second mode to exit from. Still 2 points. That's odd.
I got 4 points.
It's the color. It could be the scale. The scale is in steps of 1. Let's try y scale as 0.1. Let's see if we're able to see it. Still just 2 points. 0.7. Check the mode. We have it in normal, sequential, radius, everything looks right here. So since the calculator failed us, I don't know why, I've created a sequence of x values, which would be the indices here, 1, 2, 3, all the way up to 50. I'm evaluating psi and y, so the y values will give us psi. Psi naught is 1, psi 2, excuse me, psi naught is 1, psi 1 is 0.7997, 0.73997, and so forth. And if I plot this, that's what I get. Isn't that nice? Better than the calculator, definitely. So what do you see when you look at this picture?
What is plot gauge?
Huh?
What is plot
You
gauge?
should know that by now. I took my class.
I think you actually just wrote everything out here. And just wrote H.
Plot H would put a line this way, a stem top, right? Instead of just plotting points, it is going to give us stems. So we're looking at this picture, and what can you say?
It sort of looks like an exponential decay.
It's decaying with respect to or using these values, correct? Last time I mentioned, whatever you are today is merely a it's a combination of random things that happen to you over the past 50 days or 50 weeks, etc. and so on. So this is you today, right? Whatever happens to you today, you're fully correlated with that, right? It's random. Now, as you go to yesterday, you decrease a bit. You don't take that much effect. Another day, you decrease furthermore. Keep on going. I don't care about what happens in day 50, right? The effect of day 50 in the past is going to be very, very tiny compared to what happened more recently. Do you agree?
In most cases.
Huh?
And then in most cases.
Well, in a realistic, stable case, if you're an unstable person, then this would be flat. Right? I brought that up for a very reason, but for a very good reason. That is actually the definition of stability of a model. A stable model, a model that is predictable, will satisfy this pattern nicely. Later, we know what an autocovariance or autocorrelation function is. When we plot that autocorrelation function, we've got to see a pattern like this. So I gave you the values 0.8 and 0.1 when we first started this problem. That resulted in this graph. Yes. Now our objective is to look at a time series, get a correlation function, because this simply says today is correlated with yesterday, day before, and so on. So this is a correlation function. I can work backwards, correct? So if I work backwards, eventually I'm going to get the estimators 0.8 and 0.1. Not exactly, but close to that. Does that make sense? That's the purpose of time series. If you didn't have a pattern like this, the model is very unstable. You can't fit it. So we have the values of psi written here, computed using the calculator. In this class, we typically would not go past 6. It's just we know the concept that it's going to decay and stable. So
It's size 0, only going to be 1.
yes.
J is the theory of the point where that correlation will never, right?
Yes. So if J keeps on increasing, it becomes 0 eventually. So this would be in my example that they were looking at in the past. So YT, I can write it in terms of this size. 1 times WT, noise today. You're fully correlated with the noise today, right? Yesterday, 0.7997. Day before. Day before that. Before that. Dot. Good. Oh, I forgot WT minus. Good. So I took the process today that could be you, expressed it purely in terms of noise. In practice, this is what we call the error. This is an MA infinity model, which we'll talk about later on. Moving average WTs. Later on, I think the book uses the notation either E or epsilon. So it'll come to me. So we have this expression where we relate y sub t to w sub t, and the coefficients will eventually decay. So what is the size at polynomial? It would just be this. If I rewrote that, yt would be no lag here, correct? So L raised to the power of 0, so 0.7997, lag of 1, so .73997 L squared WT, 0.67197 L cubed WT. You get the point, correct? I'm trying to get back there. So YT have a WT in common. So I can pull that out. So 1 plus 0.7997 L, 0.73997 L squared, 0.67197 L cubed, dot, up to infinity, WT. Good. What did we traditionally do? We simply took L, replaced by Z, conjugate polynomial, right? So if I replace that, I'll have 1 plus 0.7997 Z plus 0.7399 Z squared, 0.67197 Z cubed, dot, WT. Correct. So look at that and tell me what size it is. I'll give you a hint. So this is what we have, right? And this is what I wrote. So my question to you is, what is psi z? All of that, right? So 1 plus 0.7997 z plus 0.7399 z squared, 0.67197 z cubed, dot. Good. Now you understand the process behind a second difference equation. If we understand this thoroughly, we can understand an MA1 model, MA2 model really well. So do we understand the relationship between phi and psi? Do we understand how we find the psi values? How we find the phi values? Later on, our objective is to estimate the phi and psi values. And typically, if we know the phi values, we can find the psi values. Do you agree? I started here, I ended at that. Always easier to do that. And typically, people would say, fitting an AR model is easier than fitting an MA model. That is true because of this. The left-hand side is easier to take care of compared to the right-hand side. Here it decays very, very slowly. Do you agree? Even in the graph, it didn't decay rapidly, it was very, very slow. So, you know, if this is a person, the person is regressing a lot in the past, you know, very slowly. The reason for that is in the original model itself, the original equation that I gave you. Yt is equal to 0.8 yt minus 1 plus 0.1 yt minus 2. In a simple way, 80% you rely on yesterday, and 10% you rely on the day before. Now that's too much, right? 80 and 10. If I started with, you know, 20% yesterday, 10% the day before, 0.1% the day before that, I will decay rapidly. Does that make sense? So, good. So the picture we did has a direct connection to the autocorrelation function. Our objective is to understand this process and do everything in reverse. So we start with the data to autocorrelation to finding the fees, the size, using the algebra that we have. Does that make sense?
Wouldn't 0.8 to 0.1 be